Discover Geography, Lesson 2-2, Projections. A projection is a way of taking the round Earth and putting it on a flat piece of paper or a flat computer screen. And there are a whole variety of ways to do this that have different properties. And so this lesson is going to discuss the different ways that we can create projections and the advantages and disadvantages to a variety of well-known projections that you may encounter throughout the rest of this class and outside this class. The first thing to remember is that the projection, since it's the way of taking the round Earth, putting it on a flat piece of paper or screen, is really about the shape and size of the different areas on the map. So what you see here are 4 different maps that all use the same projection. So the projection has to do with the shape of the land areas. You can see each continent is the same shape. The map as a whole is that same oval shape in all 4 of these, even though the content of the maps, what they're showing, is completely different, whether it be major cities or empires in the world in 1754, GDP per capita, or percent of native people with blood type A. So wildly different things that we can put on the map, but all 4 of these maps are using the same projection. So what is the shape of the Earth? Well, when we look at the Earth, it looks like it's a sphere. It looks like a round ball. But the Earth is not actually a sphere. The Earth is a little closer to what we call an oblate spheroid. So this is like a sphere that's been squished from the top and the bottom. So the poles are kind of flattened out and the equator bulges out a little bit on our Earth. So the Earth is actually slightly larger around at the equator than it would be going from pole to pole. But the Earth is not exactly an oblate spheroid either. It's a little lumpier and bumpier and weirder than that. So what you see here is an exaggerated representation of the shape of the Earth, so that you can see how certain areas in red kind of bulge out more than they would be expected to. Other areas in blue are kind of squished in more. And we call this shape a geoid, which literally means Earth-shaped, because the Earth is the shape of the Earth. Nothing else is really precisely that shape. And so that's not super helpful to say that the Earth is Earth-shaped. For our purposes in this lesson, the Earth is close enough to a sphere to get along with. If you get into detailed cartography, if you were to take a cartography class, for example, you would have to deal with the geoid. You would have to deal with the fact that certain parts of the Earth actually bulge out farther or are squished in farther than you would expect from a simple sphere or even oblate spheroid. But for the purposes of this lesson, we can basically treat the Earth as close enough to a sphere. So if we have a roughly spherical Earth, we can give coordinates for any location on that Earth by a combination of what we call latitude and longitude. So latitude will measure how far north or south you are from the equator. Longitude will measure how far east or west you are from what's called the prime meridian. And so with these 2 coordinates, which are both given in degrees, you can pinpoint the location of any spot on the Earth. So for example, right now, I'm located at 40 degrees, 27.459 minutes north, and 80 degrees, 0.058 minutes west. The latitude, which measures your distance north or south from the equator, you can think of as the angle between 2 lines. One line that runs from your location to the center of the Earth, and another line that runs from the equator to the center of the Earth. If you were to slice the Earth in half and measure the angle between those 2 lines, that number of degrees would give you your latitude. So we can see that 0 degrees would be the equator. Right? There's 0 angle between a line from the equator to the center of the Earth and another line from the equator to the center of the Earth. Whereas the poles would be 90 degrees. So if you have a line going straight in horizontal from the equator and one going straight down vertical from one of the poles, that's a 90-degree angle, right angle. So your latitude is always going to range somewhere from 90 degrees north to 0 degrees at the equator to 90 degrees south. And any latitude measurement aside from the equator is going to have either north or south after that. Longitude is measured in a somewhat similar way. You have the angle going from your position to the center of the Earth and then a line from the prime meridian to the center of the Earth. If you measure that angle, you get your number of degrees longitude, and longitude will be east or west from that prime meridian. Now with latitude, we had a natural starting point at the equator and a natural stopping point at the poles to define it. Longitude doesn't have that natural starting and stopping point. And so for a long time, various map makers would put the prime meridian, that 0 degrees longitude, at whatever place they felt like it, usually the capital city of their country. In 1884, the various scientific societies of the world got together and decided, let's agree on a prime meridian that we're all going to use, so we can all give the same coordinates for longitude. And they ultimately decided to make that prime meridian, that 0 point for longitude, run through the city of Greenwich, England, where there was the Royal Observatory. It was one of the foremost scientific institutions in the world at that point. So they decided that made a good reason to put the prime meridian at that particular location. And so now all other locations can be measured in degrees east or west from the prime meridian. And you can see that those degrees can go all the way around to the opposite side of the world. So your maximum longitude would be 180 degrees. Anything other than 0, 180 is going to be degrees west or degrees east. When making maps, we also have to factor in the difference between true north and magnetic north. So if you have a compass, the arrow on that compass is going to point northward, but it's going to be pointing towards the magnetic North Pole. This is the northern end of the Earth's magnetic field. And that's what pulls your magnetic compass into that alignment. But magnetic north is not exactly the same as true north. True north is defined by the Earth's axis. The true North Pole is the point that the Earth is spinning around as we spin on our axis. So the magnetic North Pole is located somewhere in northern Canada, and it actually has moved over the years. So you see on this map how the magnetic North Pole has drifted over several centuries. And so if your data is based on magnetic measurements, based on compass measurements, you have to correct for the fact that magnetic north does not point to exactly the same spot as true north. We often see diagrams on maps that are meant for navigation. So a map that you might be using with a compass to find your way. We'll have a little diagram like you see to the right there showing the difference between magnetic north and true north so that you don't get confused and don't get lost based on the difference between those two measurements. So once we can measure where things are on the Earth, we can then take those coordinates and transcribe them into a flat plane to create our projection. The key thing we have to remember here is that no projection is perfect. If we imagine trying to peel an orange and flatten out that peel, we're going to find that we're going to have to squish parts of it, we're going to stretch parts of it, and we're going to break parts of it. And that's exactly what we have to do to the surface of the Earth to create any projection. And so when we're looking at a projection, there are a variety of different questions that we can ask that will tell us what the properties of that projection are. So are the sizes of things still correct once we've squished and stretched and broken the surface of the Earth to flatten it out? Are the shapes of different areas, land areas and water areas and so forth, are they correct? Are the compass angles that you would measure from the map correct? Are the distances between places correct? Are they the right ratio to each other on the map as they are in the real world? And where is the map interrupted? That is, where is it broken? Every map is going to have at least one interruption, at least one split in the surface of the Earth to get it flattened out. Some maps have more than that. So let's take a look at one famous projection called the Mercator Projection. The key property of the Mercator Projection, the thing that makes this projection useful, is that any straight line you draw on this map is what we call a loxodrome. This is a line of constant compass bearing. So if you draw a straight line between 2 points on the map, and you measure the angle of that line with a protractor, that is the compass angle that you would follow. If you look at your compass, you correct for the difference between magnetic and true north. If you head off at that angle, according to your compass, you're going to follow that line on the map. So So you can see how this map would be very useful for navigation. If you're a ship sailing across the ocean and you want to be able to use your compass to navigate to the port you're headed to, having a map that you could easily measure those angles off of is very useful. However, in order to get that useful property, we have to sacrifice other things, such as the sizes of different areas relative to each other. So when we look at the Mercator projection, one good way to identify a Mercator projection, to know you're looking at a Mercator projection, is to compare the sizes of Greenland and Africa. On the real Earth, Greenland is about 1/6 as large as Africa. But on the Mercator projection, Greenland looks the same size as Africa. So we've had to sacrifice accurate relative sizes of things in order to get that special property that you can accurately measure compass angles off the map. Here's another very useful projection called the Gnomonic Projection. On the Gnomonic Projection, any straight line that you draw is what we call a great circle. A great circle is the shortest path between 2 points. And so we can use the Gnomonic Projection along with the Mercator projection to navigate. So for example, imagine that we want to fly from London to Tokyo. If we draw that path on the Mercator projection as a straight line, that gives us the compass angle that we'd follow if we wanted to just take one compass bearing and set off straight in that direction. We would get to Tokyo. However, if we transcribe that line, you can see how it clips across the top of the Black Sea and the top of the Caspian Sea and then goes across China. If we transcribe that to our Gnomonic projection, we can see that that's not the shortest route. That takes you kind of a loop out of your way. If we draw a straight line between those two cities on the Gnomonic projection, we can see that the shortest path between London and Tokyo, assuming we're flying so we're not worried about terrain or anything, actually takes us up across Siberia and Scandinavia. If we transcribe that back onto the Mercator projection, we can now measure the compass angles we'd need to follow if we wanted to go along that green path. The Mercator projection is clearly very useful for navigation, but because it distorts the sizes of places to a really dramatic degree, it's not really a good map for any other use. And yet, for reasons that I don't entirely understand, the Mercator projection became very popular as just a general purpose world map. So you see here an example from a Rand McNally Atlas of the World. Just for a general reference map of the world, they used the Mercator projection. This was criticized not just because the Mercator projection isn't designed for being a general reference map, but also because when you look at what areas are exaggerated and what areas are shrunk down on the Mercator projection, people notice that, well, it's the rich and powerful countries in the world that look bigger and therefore more important in the Mercator projection, whereas poor countries are made to look smaller and less important. And so if you spend all your time looking at Mercator projections of the world, you're going to get a distorted idea of what countries are big and important and what countries are not. And so people began to say that the Mercator projection was not just not a useful projection, but it was actually unjust, that it was encouraging an unjust view of the world. So one projection that was proposed as an alternative was what's called the Gall Peters projection. The Gall Peters projection is an equal area projection, which means that the sizes of areas on the map are correct relative to each other. So if you look at Greenland and Africa, you can see that Greenland on the Gall Peters projection is about 1/6 the size of Africa. However, the shapes of these areas are quite distorted. You can see that Africa looks stretched north to south, like the other areas along the equator. Greenland is very obviously squashed out side to side. In real life, Greenland is much longer north to south than it is east to west. On the Gall Peters projection, it looks like it's very wide east to west and not very tall north to south. So the Gall Peters projection is an equal area projection, but it's not a great equal area projection. Luckily, there are other equal area projections out there that do a much better job on the shapes of things while maintaining that comparability of the sizes of different areas. So here's the Moloide projection. This is an equal area projection, Everything is the right size relative to each other, and the shapes are a lot better than the Gall Peters. You can see Greenland looks taller north to south than it is east to west. The Malawide projection can easily be identified because the outer boundary of the map is an oval. Here's another equal area projection, the goods interrupted hemolysis projection. And so on this map, the shapes of things are even better than they are on the Malawide projection. If you look back at the Malawide projection, you see that the Americas, for example, kind of bow out to the west and then curve back to the east in order to fit within that oval. In the goods interrupted hemolysis, the Americas are nice straight up and down, as are the continents in the eastern hemisphere. However, to achieve this, the goods interrupted hemolysis projection is interrupted. You see those big breaks in the ocean where the map has been separated in order to try to keep the shapes of the continental areas correct and maintain their correct sizes relative to each other. So the goods interrupted hemolysis projection is not going to be very useful for mapping anything that occurs in the ocean. Though, of course, you could make a goods interrupted hemolysis where the interruptions are at the land areas and the oceans are kept together. So if you're going to map something that's just found in the ocean, you might use that alternative goods interrupted hemolysis projection. If you're mapping something that occurs on the land and the ocean, then you might want to use something like the Malawide that has only the one interruption. Another common projection is the Robinson projection. The Robinson projection is a compromise projection. It's a compromise specifically between keeping the compass angles right and therefore keeping the shapes pretty close, as you would see on the Mercator projection, and keeping the sizes of things correct relative to each other. So you can see the Robinson projection is close in terms of compass angles, but not quite there, and it's close in terms of correct areas, but not quite there. So this is useful for a general reference map of the world. If you don't need either the compass angles or the sizes of things to be exactly right, you just want to get in the right ballpark on both of them rather than getting one exactly right while wildly distorting another, Robinson projection could be a good choice. And you can identify a Robinson projection because the sides will be curved, but the top and bottom will be flattened off. Another similar projection is called the Winkel triple projection. It has that same shape of the flat top and bottom and the curved sides. It's just a slightly different level of compromise. There's a slightly different balance between correct areas and correct compass angles on the Winkel triple. The Winkel triple is the standard projection for world maps used by the National Geographic Society. So you'll see this one a lot as well. The last projection that we want to talk about is the azimuthal equidistant projection. The azimuthal equidistant projection is a projection that keeps distances correct. Now you can't have a projection that keeps all distances correct, the distance between any 2 points to be accurately measured. But with the azimuthal equidistant projection, you can accurately measure distances from the center point to any other point on the map. This is often used for things like targeting missiles, watching for airplanes coming into an airport, or examining broadcasts of radio, where you need to be able to measure the distance from a fixed point. So in this case, these are radio stations, transmitters. You need to be able to measure the distance from that transmitter to any point that you might be transmitting to. And so you create an azimuthal equidistant projection that's centered on that transmitter. And so in this case, this is a map that I generated that is an azimuthal equidistant projection centered on the transmitter for WESA, which is a radio station in Pittsburgh.